Hello, today we're going to explore what many call the most beautiful formula in mathematics. It's known as Euler's identity. By the end of this video, you will be able to 1. Understand how to calculate e to the power of a complex number, and 2. Explain why Euler's identity is so special by connecting it to two fundamental mathematical concepts. Here is the identity. Look at it for a moment. What do you notice? This single compact equation beautifully ties together 5 of the most important constants in mathematics. We have e, the base of the natural logarithm, an irrational number that starts with 2.718. We have I, the imaginary unit defined as the square root of -1. This introduces us to the world of complex numbers. Then there's p, the ratio of a circle's circumference to its diameter, another famous irrational number. And of course, 1, the multiplicative identity. Multiplying anything by 1 doesn't change it. Finally, 0, the additive identity. Adding 0 to anything doesn't change it. This identity shows a deep and unexpected relationship between these seemingly unrelated constants. A great way to understand the heart of this identity is to build it from another, more general formula called Euler's formula. In this scene, our goal is to understand Euler's formula, the foundation for Euler's identity. Let's first get comfortable with the concept of the complex plane. You're likely familiar with the standard coordinate plane with an x-axis and a y-axis. The complex plane is very similar. The horizontal axis, or the x-axis, is called the real axis. The vertical axis, the y-axis, is called the imaginary axis. We can plot any complex number, say z equals a plus bi, by moving a units along the real axis and b units along the imaginary axis. Notice that we are essentially creating a point, AB. This point has a length from the origin, which we call r. We can also describe it with the angle it makes with the positive real axis, which we call theta. Remembering trigonometry, we know that the real part, a, is equal to r times the cosine of theta, and the imaginary part, b, is equal to r times the sine of theta. So, our complex number z can be written as r times the quantity cosine of theta plus I sine of theta. This is the polar form of a complex number, describing it with a length and an angle instead of an x and y coordinate. We're now ready for our main objective, to introduce Euler's formula. Euler's formula provides a profound and beautiful connection between complex numbers and exponentials. It states that e to the power of I times an angle theta is equal to the cosine of theta plus I times the sine of theta. This formula is a bridge connecting exponential growth on one side, represented by e, to circular motion on the other, represented by cosine and sine. It tells us that raising e to an imaginary power is fundamentally an act of rotation. Think back to the polar form we just saw. Z equals r times the quantity cosine theta plus I sine theta. Euler's formula shows us this is the same as r times e to the I theta. Let's visualize this. In the complex plane, e to the I theta is a complex number that lies on the unit circle, a circle with a radius of 1. As the angle theta changes, the point e to the I theta spins around this circle. If theta is 0, we are at the point 1 on the real axis. As theta increases, say to p over 2 or 90 degrees, the point rotates counterclockwise to the top of the circle, landing on the imaginary axis at the point I. For this scene, we've successfully introduced Euler's formula and visualized its meaning. We've seen that it connects a complex exponential to a rotation in the complex plane. We have arrived. In this scene, we will derive Euler's identity directly from Euler's formula. Our objective is to calculate e to the IP. This is the core calculation we need to perform. We'll use the formula we just learned. Here it is again. E to the I theta equals cosine of theta plus I sine of theta. For our calculation, the angle we are interested in is pi radians. So we need to set theta equal to pi. Now we substitute pi for theta in Euler's formula. This gives us e to the IPI equals the cosine of pi plus I times the sine of pi. Now let's take a moment to recall the values of these trigonometric functions. The cosine of pi is 1 and the sine of pi is 0. Now we substitute these values back into our equation. This gives us e to the IPI equals -1 plus I times 0. And simplifying, anything multiplied by 0 is 0. So e to the IPI equals -1. We have just performed our main calculation. Let's make it look like the standard identity. We can add 1 to both sides of the equation. On the left, we get e to the IPI plus 1. On the right, -1 plus 1 is 0. And there it is, Euler's identity. E to the IPI plus 1 equals 0. We've achieved our objective and successfully derived this famous formula. Now for our final objective. Let's take a moment to appreciate why Euler's identity is considered so beautiful and important. We will explore two key reasons. The first reason is that it brings together these 5 fundamental constants of mathematics in a single, simple statement. It links E, which describes continuous growth, I, which introduces the plane of complex numbers, P, which is at the heart of geometry and circles, and 0 and 1, the foundations of arithmetic. The second reason is its geometrical interpretation. Let's animate the process in the complex plane one last time. We start at the point 1 on the real axis. Multiplying by e to the IPI is equivalent to rotating this point by an angle of pi, or 180 degrees counterclockwise. After this rotation, the point lands precisely on the real axis again, but this time at the point -1. Our calculation, e to the IPI equals -1, is simply a mathematical way of stating that a 180-degree rotation of the number 1 results in the number 1. It's a statement about rotation. So, to recap, Euler's identity is special because it unites fundamental constants and provides a compact way to describe a 180-degree rotation. Let's quickly review what we've accomplished today. We started with the beautiful statement of Euler's identity, e to the IPA plus 1 equals 0. This identity shows an unexpected and profound relationship between 5 of the most important constants in mathematics. Our main objective was to understand how to calculate e to the I theta. We did this by understanding the complex plane and Euler's formula. Euler's formula, e to the I theta equals cosine theta plus I sine theta, showed us that an imaginary exponential is equivalent to a point rotating around the unit circle. By setting theta to pi, we derived Euler's identity, which is a mathematical expression for a 180-degree rotation of the number 1 to the number 1. Thank you for joining me on this exploration of Euler's identity. I hope you now see why it holds such a special place in mathematics. If you'd like to dive deeper, you might enjoy this animation that beautifully illustrates Euler's formula using the concepts of exponentials and circles.